All right, welcome to video number 2 in our video series on motive technology, and this particular video is going to sort of extend where we talked about in the first video, but we're going to get more into detail specifically about electromagnetism. So in the first video we sort of generalized the forces in the universe, and we generalized that there's stuff in the universe, so matter and stuff that happens to matter, energy and forces. Energy, forces, which are essentially the same sort of thing, and matter, which is the stuff in the universe. Electromagnetism, and this particular video is designed to take that first video, which really structured electricity in terms of the entire car or motive system. This video is going to take that and go into a little more detail about electromagnetism, specifically in a vehicle. But we're not going to go into detail about things like starter motors, AC generators, specifics in the car. This is going to position the viewer to understand electromagnetism in the context of the car, and subsequent videos will have probably a more detailed, specific to the car electromagnetism. So let's start with that. Now, we remember that in the last episode, before we start, a word from our sponsor. The sponsor of this video, in other words, giving me some money so I can do these videos, is Buckshot Feminine Hygiene Products. Okay, so Buckshot Hygiene Feminine Products. They're addressing a market that is not addressed. If you're a sporty woman who likes all natural goods and you've got heavy flow, Buckshot Feminine Hygiene Products. Hey, if not you, then who? Okay. So, electromagnetism. We discussed last episode that the universe is divided into two sort of things, very generally: matter and energy. Energy, which is a bad spelling of energy, but I'm sure you know what I mean. So matter is the stuff, and energy, or forces, is stuff that happens to stuff. And we learned very quickly, that the types of energy, of course, are, we have electric, we have magnetism, of course, we have gravity, and then two different forces. We didn't get into very many of these forces. We got into, there's the strong and the weak. Those are the other two forces. They're distinctly different: strong, weak, nuclear force. And we discuss, so here are the forces that happen to the stuff, so forces that happen to matter. We very recently, or last episode, we briefly mentioned gravity, and essentially it's not going to come into play into automotives. We briefly mentioned the strong and weak nuclear forces. They are definitely not going to come into play for motive technology. And then finally we mentioned electric and magnetism, and we also mentioned that the electric and magnetism were unified. So these are unified into electromagnetic. And all it means to be unified, is that the same fundamental equations. The same math can be used to describe both the electric and the magnetic forces. And this happened, as I mentioned in last video, around 1890, the late 1800s, and eventually too in the 1990s, the weak nuclear force was also combined with the electric and the magnetic force. So now we have three of the fundamental forces that are all described by the same math. Okay, so today, as I mentioned, we are going to be talking about the electric and the magnetic force combined, and that becomes very important when discussing motors. So essentially, we will be talking about the electromagnetic force. Now, anytime we talk about a force, we have something called force fields. So a force field is just like, okay, so here you're looking at, can be anything. We're just going to say that this is an area of space. Here's some space, okay? This is space. And let's just pretend that we want to examine the field that exists in this space. Well, what kind of field are we looking at? Well, we're going to look at heat. So here we have, I'm going to make this red again, here we have a nice little fire burning in our fireplace. There's our fire. It's burning in our fireplace. We've got some logs, and it's burning. Now, what's the field? Let's take a field of temperature. So here's our fire burning in our fireplace, and we're interested in the temperature field. Well, that's easy. The temperature field of the fire is just whatever the temperature is at every point in space. So this point in space right here has a temperature. This point in space right here has a temperature. This space right here has a temperature, etc., etc. Every single space has some temperature. Now, well, the temperatures might be very, very similar between T1 and T2, but in any case, doesn't matter. They can be exactly the same, but the value of this temperature field at this spot is whatever T1 is. At this spot, it's whatever T2 is. And we will then be able to say, okay, there's a temperature field, and really it looks like whatever the distance away from the fire is, this has a very high temperature, and it seems to be that the further away you get from the actual fire, the lower the temperature drops, and that's sort of how a temperature field behaves. Well, there is, of course, also an electric field, and there is a magnetic field. So we have an electric field, and we have a magnetic field. So electric field and a magnetic field. So magnetic field. Here, I'll write that properly. I'll undo that and write that properly. Magnetic field. Okay, so what's an electric field? Well, an electric field is anytime current is passing through something. So let's say we have here. Let's draw an magnetic field. An electric field right here. So if we have a wire, here is a wire moving along. If we have a wire, then and we shoot electrons along this wire, electric. This electric field is moving. The flow of electrons will go that way. So this electric field is moving. That's an electric field, and if current is flowing through it, so there is some amperage, which means that there are electrons moving through it, this is the electric field. And just like the electric field of a flash of lightning exists around this flash of lightning. The electric field exists all over space. So this electric field around this wire will actually exist even outside the wire. However, it's so tiny, it's irrelevant, especially considering that most wires are insulated, which is something that's non-conductive. So in this case, we have an electric field that's in existence. In our little example, it's moving in one direction because there's amperage going through the wire, and because it's moving in one direction, and not just sitting still, we have an electric field. Same sort of process with lightning, but the electric field is very contained within that bolt of lightning, and even though it's not insulated, the electric field does extend outside of the flash of lightning, but it's really, even though it doesn't have insulation, it's still inconsequential. So electric field you can see in a flash of lightning, or you can just know that it's existing in a wire with current flowing through it. Magnetic field is similar. So let's say you have a magnet. Let's pretend you have a magnet. So here is a magnet. And this is a bar magnet, and this is, we'll look at it in a second, but this is a permanent magnet. So this is just a chunk of metal. And here is the North Pole, and here is the South Pole. Now, magnets also have force fields, or they exert or create force fields around them. Just like an electric wire, for example, can create an electric field within itself, a magnet also has lines of force. And the lines of force from a magnet come out of the, let's say, out of the North Pole and wrap around the entire magnet like this. And then there's another line of force that wraps around the entire magnet like this. And of course, those lines of force extend around the magnet on all sides in these big, ever-expanding loops. And for example, if you wanted to see examples of the line of force of a magnet, all you have to do is take a magnet, like a fridge magnet, and sprinkle like you're sprinkling some icing sugar. Just sprinkle it all over the magnet, and you will see the little iron shavings or iron filings will align themselves along these lines. It won't be perfect, but you'll at least be able to see the force lines. And that's an example of a magnetic field. So, in the magnet, so we have really two types of magnets. I just gave you an example of one type of magnet, which is the permanent magnet. So here's a permanent magnet. It's just that bar of metal that you're used to. Here's the bar of metal. It has a North Pole, and it has a South Pole, and this is a permanent magnet. What permanent magnet means is essentially, this is a magnet, it's natural. In other words, you could be digging around in your backyard or walking along or looking on your fridge, for example, and seeing something stuck to it. There's a piece of material that sticks to other pieces of material without glue, and that is a magnet. So you can find permanent or natural magnets all over the place. Like literally, if you dig in your yard, you might find a chunk of rock or something that is magnetic, and it doesn't lose its magnetism. It's just magnetic all the time. Like a needle in a compass, for example, always magnetic. Permanent magnet, it does not require any electricity. Then we have a different type of magnet, and that's the electromagnet. So we take a bar, let's just pretend it's a bar, just to make it easy. We take a bar, but it can be anything in the world, any material in the world. Here's in our case, a bar. And we're going to call this any material in the world. And we are going to take a wire and cause current to flow through it. And since we can't just have one wire, we need another wire with the current going out of it. Now, the current going into the wire and then subsequently coming out of the wire, it's going to turn this material, it's going to electrify this material, which then magnetizes this material. So as this current flows through the magnet, it will create a magnetic field that exists around this magnet. Now, I shouldn't have drawn the magnetic field lines where I did, they go around the magnet, so I should not draw them behind. See, here are the magnetic field lines, they're going through the magnet. Why are they going through the magnet? Because we have charged the magnet. We have attached wires to it that carry a current of electricity or electrons moving through the material. Now, this material, this will turn any material into a magnet. Now, not all things make good magnets, but you could, in theory, attach a wire to one end of your body, a wire to the other end of your body, run a current through it, and you will be magnetized. However, you are not made up of stuff that's very easily magnetized. Therefore, before you become walking around picking up everybody's paper clips, you'll probably die. Because your material, whatever your body is made up of, it's not a very good magnet. And this leads us into the other example, this leads us to further clarify exactly what an electromagnet is. So when we have, if I say any material can be turned into an electromagnetic magnet just by pumping in electricity, well, some materials like the electricity better than others. So let's take a look at this mystery material here. Here's a mystery material, and this mystery material is composed of atoms, molecules, whatever, but it has constituent parts. Let's call it atoms. It doesn't matter what you call it. You can say that this material is made up of constituent parts, smaller chunks of this material. If you want to think of it as atoms, that's fine. So we have something that this is the material. This whole thing is the material. And this little guy in here is a constituent part. This is a constituent. So again, constituent. So again, think of an atom. It's not the correct way to think of it, but the smallest part of whatever this material is, it will have, so let's call it an atom. The smallest part will have a polarity. It will have magnetic properties that are either aligned north or aligned south. So the constituent components of whatever this material is, they will have a polarity. Maybe the next door constituent component looks like this, with the north going down and the south going up. And maybe this one is completely sideways, with north here and south here. Now, if I run my electricity through this mystery material, here comes my charge. I'm running a current through here, and of course the current has to go somewhere, so the current is coming out. If I run a current through here, and these constituent components stay the way they are, this material will become electromagnetized to some degree, but not very much. It's not doing anything because the current or the charge, it doesn't really want to be a magnet. The charge, it would require significantly more charge to get all these constituent components polarized in the same direction. And so you say, okay, let's increase the charge. But essentially, if this mystery material were your body, you could increase that charge to 1,000 amps and then run it through your body. It's going to kill you before it aligns all your constituent components and polarizes you. However, if we run the electricity through this piece of material and it's not your body, and running this material through here causes all the constituent components to line up in the same direction. So here are the constituent components of this material. Again, think of it as atoms or the smallest chunk of whatever the material is that you have left. It lines up all the constituent components in the same direction. And that, dear viewers, that is a good electromagnet. So again, we're pumping electricity through. It is a very highly magnetic material, and this electricity running through this material causes its constituent components to all line up in the same direction, and lo and behold, we have an electromagnet. And when we have this electromagnet, we have all the atoms or all the constituent components running in the same direction, and lo and behold, we now have our lines of force very, very weakly. They're very weak because in my example, I'm not running much current through here, and you'll see why in a second. So, and again, these lines of force are going out this side as well. Magnetic force. The electric force field is contained within this wire. It's also contained within this material and contained within this exiting wire. And the magnetic force, when all the constituent components of the electromagnet are lined up in one direction, they will come out of the north side of the magnet and go right around the magnet and go to the south side. Up here, they were pointing, the constituent components were pointing in all sorts of different directions. So we had, maybe a line of force going like around it like that, maybe another line of force going around. Oh, this one was pointing here, so the line of force is going, a weak line. Here we've got a much more directed set of lines of force, again, because everything's pointing in the same direction. Everything is polarized the same way, so the lines of force are going the same way. Now, what makes so the strength of this magnetic field is very important. And when we talk about strength of a field, so remember, we have field strength. So remember, when we talk about how strong the yellow magnetic fields are, when we talk about how strong those are, we need something to describe it. When we just talk about electricity, we talk about the electric field, or the EF, the electric field. We talk about amps specifically, and maybe volts, but volts is more of a difference in electrical potential between two spots. Amps is the amount of current at any one particular spot. So amps is better, but to some degree, voltage can also be used to describe an electric field. But when we talk about magnetism, we don't use the terms amps. Magnetism. Here, we're talking about MF, and that stands for magnetic field, not Farmer. But the magnetic field is measured in flux density. So something with a high flux density, that's a strong magnetic field. And if you have a low flux density, that's a very weak magnetic field. So there are some things that we can do to make the magnetic field stronger without necessarily increasing the amperage or the current that's flowing in. So again, remember from this previous diagram, this is a piece of material before it becomes this here, let me move over. This was an example of two electromagnets. This electromagnet had a current, let's say a weak amperage current going through it. It did not cause the constituent components to all line up in the same direction, i.e. get polarized. Therefore, it does not make a very good electromagnet. This particular material did have components, constituent components, that did line up when a current was passed through the material. They all lined up in the same direction, causing a more efficient and stronger magnetic field. Not much stronger, but it's still stronger. And that increases the flux density automatically because the thing wants to be a magnet and you're running electricity through it. But both of these examples are indeed electromagnets. Now, when we're talking about the strength of the magnetic field, we're talking about flux density. And if we want something to have a higher flux density, absolutely we can shove or pump more electricity through it, but that's not necessarily the answer because that is wasteful. So instead, we take our magnet. Here once again is our magnet. And I should say that this is our electromagnet. And instead of attaching the wires here and an exiting wire, let's say here, that's totally fine. But we can be smart about it. We can take this wire, here and wrap it around. Constantly wrap it around. Now I'm drawing nice big spaces in the wraps, but in real life you would wrap these extremely tightly together. So in real life you would wrap these wires around the coil extremely tightly together. Now what's happening here? Remember I said these wires do produce a little magnetic field out here. Now we take the insulation off these wires so that the electric field generated by these wires, it kind of goes in circles around the wires. And you can see, since there's no insulation on the wires, that obviously means the electric field that surrounds the wires penetrates the material that's trying to be turned into an electromagnet. And this creates much more magnetic field penetrating into the material that wants to be an electromagnet, which has the same effect as just taking electricity, running it through this side and picking it up out of this side. Except this is more efficient because A, the material may be a good magnet but not a good conductor of electricity, and this will overcome that problem. And you can use the same amount of amperage to produce a higher magnetic field, or a magnetic field with a higher flux density. And then once again, your lines of magnetic force will be coming out of this magnet here, but they will be much stronger. They will go around the magnet just like we showed before. They go around and around and around the magnet like that. Around all sides of the magnet. So that's the way we use efficiency to line up, that's the way we use not just increased amperage, but increased efficiency, winding the coil around the material that you want to electromagnetize. We have that producing more flux density. So current increases flux density, the greater is directly related. The greater current, the more flux density, and the number of windings around an electromagnet increases flux density as well. Directly related. Now, remember too, if we go back here, we said, hey, we can measure field strength. Well, we also can measure material resistance. So here, let's say material resistance. So remember, in electricity, you could attach a load to so in electricity, you could attach a load to a circuit, let's say, attach a light bulb to a circuit, and that light bulb, that load that you're attaching to the circuit will resist the passage of electricity to some degree, or maybe it will not resist it at all. In any case, the level or amount that a particular material wants to be electrified, we've learned that in detail. Those are the ohms. That measures resistance. That is the resistance to electrical charge. In magnetism, we don't talk about ohms when we talk about resistance to becoming magnetic. We talk about reluctance. So if a material has a very high magnetic reluctance, its resistance to being magnetized when electricity is flowed through it is very high. If you have a material that has a very low reluctance when electricity is flowing through it, then its reluctance or its resistance is low. And that means it wants to be an electromagnet and will form a good electromagnet. That is reluctance, not resistance. And I believe, although I'm not sure, that reluctance is measured in henries. I think Mr. Henry got in line early for that. So, we have discussed how a magnetic field is generated by passing electrons through that field, by passing electricity through an item to create a magnetic field. That's what we discussed in this area right here. Now, one last note on polarity. Okay, so here's the one last note on polarity. Let me reiterate this very important point, because this will become important when discussing AC generators, DC generation, and starter motors, and that is polarity. So remember I said if an item is made up of stuff, constituent components that want to be magnetized, that item has a low reluctance, and its constituent components are all going to line up in the same direction and become polarized. So in my little example, I said, yeah, whatever material we're turning this electromagnet in, whatever material we're making this electromagnet out of, we're running electricity through it, and that's going to cause all the north poles to be on one side and all the south poles to be on one side. It's going to polarize the object, which results in this configuration of its constituent components. And I want to reiterate that when its components are lined up in this constituent configuration, current flows that way. So this is current, which we learned in electricity is called I, which I call C, and everybody calls different. So current flows out of the North Pole, then around, current flows out of the North Pole and into the South Pole. So that's important because we are going to learn that if you change the direction of the polarization, you change the direction of the current. And that becomes very important in AC circuits and generally throughout the entire vehicle. So let's say that so let's summarize before we move on to the conclusion. Let's summarize what we learned. So essentially we learned in theory how to make an electromagnet. All you do is find a material, preferably with a low reluctance, that allows electricity to pass through it or not, doesn't really matter, but has a low reluctance and wants to align all its constituent components in the same direction to become polarized and therefore create a strong magnetic field. A strong magnetic field. What do we need to determine, just generally, not measuring it, what is a strong magnetic field? Well, field strength. And this is pretty easy. Ooh, there's a G in strength. Field strength. This is pretty easy because there are really three things that determine field strength. It's directly related. There is a direct relationship direct to field strength versus number of coil wraps. And this is because, why is it directly related? Well, it's directly related because the more field strength you want, the more coil wraps you need. So that's directly related to each other. So this is more electric field penetrating the material that's turning into an electromagnet. The other relationship is to another direct relation to the amps, which basically, I'm going to summarize this. More electricity means more electrons, means more electric field, means more magnetic field. More magnetic field. And then finally, it has an inverse relationship. There is an inverse relationship between the reluctance is inversely related to the strength of the field. Or as we describe it properly, since we always do everything right, to the flux density. So if reluctance increases, then field density decreases. If reluctance decreases, then flux density increases. Pretty simple. Or as the point set theorist professors say, completely trivial. Okay, so to summarize now, here what we're going to do, just to wrap this all up, basic theory, electric motor. Okay, this is going to look nothing like any diagram in a motive textbook, and it's not going to get so in depth that we're talking about the differences between alternating current and direct current, or differences in the use of permanent magnets or electromagnets within starter or electrical generators. This is just basic electromotor theory. This is the fundamental of how an electric motor works for anybody, not just motive people. Anybody who needs to know. You won't be able to build your own electric motor with this knowledge, but when you're getting knee-deep into anything electric motors like starters or ignition systems, these are the basics that you have to know. We've already covered the essentials of electromagnetism, but then how do we convert electric power into motive power, and that, or kinetic energy, electric energy into kinetic energy? And that is described here in the basic theory of an electric motor. So all we have to do, it's so simple. Let's just pretend we have two magnets, and whether they are bar magnets or whether they're permanent magnets or electromagnets doesn't really matter, because we're not getting that in depth into this. So here we have two, let's call them electromagnets. So here's one electromagnet, and of course we wrap our wire around it, because what we're trying to do is create the strongest electric field possible. Here this wire's coming out and it's going away. We're trying to create the strongest electric field possible, so we have to decide whether we're going to shove in tons of current or wrap tons of coils around it, or a combination of both. And of course we want to use something that has a very low reluctance, so we get the strongest magnet we can. Maybe we'll say, just for fun, that we're trying to use the least amount of amperage as possible. And of course this wire over here is the same thing, right? Electricity is going to come in here. We are going to wrap the field coils around here a ton of times. My picture, of course, doesn't do it justice at all, and this is where the electric current is coming out, just so we don't get all pissy about a non-completed circuit. Here in the middle, and okay, so we already know this is the North Pole, And this is the North Pole here. Yeah. And here we're going, you know what? Well, we're going to make a South Pole because we have to. And South Pole is green because we're closing in on Christmas and that's fun. Here's the South Pole. And here's the South Pole. Okay. In the middle, we're going to have another magnet. This magnet has a hole in it. And lo and behold, here is the other magnet. And here we have, once again, we have the North Pole and the South Pole. Here is the North Pole. And we have the South Pole. Wrong. Sorry about that. South Pole. Okay. So this magnet is on a pivot, on a circle, on a ball bearing, on anything that allows it to spin. Right now, nothing is happening. We've just got one electromagnet on one side of this magnet and one electromagnet on this side of the middle magnet. We pass electricity through both these magnets, and in this configuration, what's going to happen here is that the north pole of the electromagnet is touching or is directly facing the north pole of the magnet that can spin. And the same on the other side, the south pole of the magnet that can spin is touching the south pole of the electromagnet on the other side. This, and electricity is turned on, remember, this is not liked by the magnet because here we have a north pole and a north pole and they want to separate. They want to separate. So this guy here, he's going to get forced. He's going to get forced down like this. And this one's going to get forced away like this because of the current flowing through here. Now, this action, and you can see this will continue, so then it flips up. And you know what? Let's just be smart about it. We're going to put some more magnets here, and we're going to put some more magnets here, electromagnets. Again, we're going to constantly keep this thing spinning. It's going to want to spin all the time. And that, although it doesn't look like it right now, but that is the basic fundamental of how to create an electric motor, how to turn a magnetic field. No, that's getting too complicated. It's how to turn magnetic energy into motive energy. Ultimately, it's how to turn electrical energy into motive energy. So we have, and the reason why we're turning it is, it's not really because this magnet here is turning. It's because of this hole that it's turning on. Through this hole, we could stick anything we wanted. So we could stick a pipe. So now I'm going to switch to sort of 3D, right? We could stick a pipe through this hole. Here's the pipe going through this side of the hole. Oh, this is a weird color. I'm sorry. So here is the pipe. It's sticking out of the hole. Then it's also going out the other side of the hole, back here, right? because this magnet is set up in such a way as to spin, because it never wants to be touching its constituent parts, we have a situation where that spinning center magnet can actually spin the pole that we stuck through it. And this pole can be attached to whatever, gears, wheels, pulleys, levers, and there we go. Now we have a situation where we have taken first electrical force, we have taken this electrical force, we have changed it to magnetic force, and changed that into kinetic energy or motive force. Kinetic energy or motive force or inertial force, however you like to describe moving motive force. And that is the very basic theoretical functionings of an electrical motor. Once we get into the actual types of motors, actual types of starter motors and electrical generating systems in the car, you're going to notice, it's not quite the way Big Al drew it, and it's totally not. It's the real engineering of these components is completely different. But this, hopefully, has been successful in teaching you guys the fundamentals of electromagnetic power generation and use. And the next video will be on starters and the differences between AC and DC power.